This should be clearly visible. Whatever I've drawn, that should be clearly.
Okay, sir. भरोसा रखें. Yes, sir. Start.
Okay, so let's get started. We had a quiz last time. I gave you 3 questions. Okay? And how did you find it? That was very straightforward, but I was surprised that some people were finding it difficult because 3 questions. This was very straightforward.
Yes.
Okay,
Yes,
some people in this one you could have just done half of it, and that would have been applicable to the other half also because the structure is symmetrical. Okay, so if you are intelligent enough, please take use of symmetry rather than you wasting your time and doing it all together. So always look for those questions in the exam which are symmetrical. Do the halfway, and it would apply to the other half also. Okay, so that's how you can efficiently utilize your time. Okay, so this one was a bit unsymmetrical. Nevertheless, it was also straightforward. In this one, I asked you to use method of joints. In this one, you were asked to use method of sections. So how would you find the sections? I mean, like, what sections? How would you assign the sections in order to analyze it?
Vertical and horizontal.
Yeah, I mean, like, it's not necessary that the section is straight. It should start from anywhere and it should cross, okay, any line. So, I mean, initially you could have done this one. You could have done this one. Straight away you could have found this one. And then after that, I mean, using these two, you could have taken the moment about this one and found these ones. Okay, and then, I mean, you could have done this one.
Yes, sir.
Yeah, and similarly, you could have done this one. So this was also relatively straightforward. This was some of the students got confused with the geometry. I think so. Geometry was pretty straightforward. You had everything known: 8 minus 5, which is 3, and then after that, finding out your angles, inclination, everything you could find easily. Is there any confusion on the geometry of this one? Any confusion? Yeah, that's fine. Okay, then we had this question. This question had an internal hinge in the middle. So, I mean, the usual way, I told you that in all of these questions, first of all, you start off from finding out your determinacy, whether it's external or internal, you find it out. Okay, you make sure that this is determinate, and then after that, stable. Okay, if the structure given to you is unstable, then you don't need to do anything about it. Just mention that this is unstable, and that's it. You don't need. I mean, you can't apply equilibrium methods on unstable structure. Okay, sir, can you please share this with us also? Something sounds very interesting. Yes. Huh? What was that? No, not sorry. What was that? What were you texting? Sorry, what was the message? Yes, please share it with us. What's that? Whose notification? From where? Look, guys, please don't get us distracted by using this. Okay. So, we had in this question. You start off from where? Finding out your indeterminacy, stability, and all that, and then after that you can use your. So if it is a determinate structure, obviously then you can employ your equilibrium techniques and you can find out your all the reactions. Okay, so clearly this is also symmetrical, so you needed to do only half of it, not the full one. In this one, what happens is that you would have a reaction like this and reaction like this. Obviously, yes? And you would have a reaction like this and reaction like this. Okay? Now the problem is, I told you, what is the significance of this internal plastic hinge? Moment is 0. So why most of you have got moments over here? Most of you have drawn bending moment diagram and you have got moments. This would have, so this is the bending moment diagram. Okay, something like this. Then you would have something like this, and then something like this, yeah?
So 500 and minus 500 जो moment sign है तो ये नीचे नहीं जाएगा.
Ah, what do you mean?
On left side 500 moment reaction था और right side पे minus 500.
Yes, so
नीचे आएगा ना दूसरी side. Yes sir.
so what will happen? What is wrong in this bending moment?
Sir, it is going up from both.
Huh? No, but you would have this reaction, okay? And this reaction would have something like this, and then yes, yes, okay. You would have a reaction over here. This reaction would have a counter reaction which is in this direction, isn't it? And I told you always draw it. It's better that you draw it on the tension side.
Yes sir.
So if you are drawing it on a tension side, so that means that it will be trying to. So this moment will try to lift it up, isn't it? So your tension, so it will be above. Yeah, and then it should come down to 0. Why? Because normally it won't come down to 0, it will come like this. Okay, normally what will happen is that you will have, if there was no hinge, then it would have come like this. But in our case, we have got hinge, so this thing won't come, we will have it on 0. And then from there it will rise again to this. Do you understand my point? So your structure analysis should have given you that. Yes, yes.
The first part ये आपने BMD बना, SFD बनाई है BMD.
No, this is BMD.
BMD. सर ये तो नहीं बनती ना. आपने हमें बताया था कि जब से perpendicular load डाल रहा होगा तब आपने BMD बनानी है. SFD BMD बनानी है. यहाँ पे कोई perpendicular load नहीं लग रहा.
No, but there is a load over there. How? This one.
This reaction is 0 sir. There is no horizontal.
This is not matter of horizontal force. This is something. If you have a load over here and you have a load over there, okay? So this would have a counter load in this direction. This would have a counter load in this direction, and this couple to counteract that, you will have. This is going in this direction. You will have a moment in this direction. What I told you was that if you don't have this horizontal one, so it was a roller. That's why I'm saying that don't try to think about the problem. If I have a roller over here, then I don't have the horizontal force, and obviously then you have a vertical force. Okay, a vertical force, no horizontal force. So this moment becomes 0.
Sir, but there is no horizontal reaction. So what is the value of BMD?
What do you mean? This load, what will happen to this load which will be counteracted by this one?
This is 0 load.
Sir, can you find these reactions?
Can we find the reactions? Because we have only 2 reactions, 2 vertical reactions on each hinge.
You have 2 vertical reactions
On each hinge.
and you don't have the horizontal one?
H is equal to 0, sir.
No. How do you know H is equal to 0?
Because there is no horizontal force acting on the member.
First of all, you have to take the global structure.
Okay, sir.
Then the global structure, you have one this horizontal force, one this horizontal force. How do you know that these both are 0? How would you know that these horizontal forces are 0? This horizontal force can only be 0 if you have on this support roller. You don't know that whether this is 0 or not.
Sir, how will we calculate it? Can you show?
Huh? How can we find it out? You have to take, you have got a third equation which is about this point. So you take moment, force this time this one and this time that one. So you get this horizontal force.
Vertical is unknown.
Sorry?
Sir, vertical force is unknown as well. So
You can take moment, this gives you an additional moment location. You can have moment equal to 0 at this point and then you can find out your vertical force, can't you? Because the horizontal force above this point is 0, lever arm is 0.
yes, sir.
You understand my point? So what I am saying is that you can take moment first of all about this point and then you can, this one will be 0. Okay, the horizontal reaction will be 0. Why? Because the lever arm is 0 above this point. So if I call it A and B. So first take summation of moment about B equal to 0. Yeah. So the horizontal one will be 0 and you will have vertical only. You can find out the vertical from here. Summation of Fy will give you the vertical over here, or either you can do the same thing, summation of moment about this point equal to 0 and you can find out your verticals. Now you have horizontal. So if it's now this horizontal, how would you find out this horizontal? Because we have got a third equation which is over here. Then you can find out your horizontal.
दोनों points में moment देके दोनों देखते हैं.
Yes, this gives you an additional equation for moment. Do you understand my point?
Yes, sir.
So that's why. So in that case, you would have this one causing this moment, and that moment will be then transferred to this member. That moment will die down as you move towards your internal hinge, and then this moment will start growing again when you reach the end of the beam, and then that will be transferred over here, and then it will die down again when you reach the other support, and that is because it's a hinge connection. You understand my point? So that's what's going to happen. Okay, so may I ask you to do these questions in assignment also, please, for me? Yeah, and I'll give you one another question for your understanding.
Excuse me, sir.
Yes.
Sir, can you please solve that question for us?
This question I'm saying that how would we find out the reaction of this one? The reaction of this one, I'll solve it quickly, you'll do it then neatly in your assignment, okay? So, I'm just quickly solving it. Summation of moment about B, you will do all the initial steps like determinacy, and that is usual stuff, so you know that. Okay, so summation of moment about B equal to 0. Okay, so we have a Y times, help me out please, 10 minus, what is this? 10. This is 10 kids per foot, isn't it? 10 into 10 into 5 is equal to 0. So AY will come out to be 50. Yeah?
Yes, sir.
And it makes sense also because this is symmetrical, so half of the load will go there and half there. Similarly, BY
will also be 50.
will be 50k using summation of k. Please avoid doing like this in the exam, okay? I'll mark you down if you do it like this. I'm just quickly give you an understanding. That's it. Okay. So the way I solve normally the problem, okay, properly, you have to give me that sort of thing. Exactly. So AY you found, BY you found. Now you find out summation of moment at A equal to 0. This is no, not A. This is what is this? I call it C. At C equal to 0. So what will happen? I will have I will have AX times, how much is that? 12 into 12. So this will be like this, and AY times 5 like this, and 10 into 5 into 2.5 is equal to 0, and this is also like this, so this is plus. Okay? Do you understand? 10 into 5 into 2.5. Yes? So AY is 50, so AX would be equal to, come on, give me.
10.42.
Is it true, please? Can someone second it?
10.4.
10.42. Okay, so that is your AX, and summation of FX is equal to 0 will give us BX is equal to 10.42 kips. Yes? Now do your usual structure analysis. You have AX equal to how much? Sorry, AY equal to 50, and this one equal to
10.42.
10.42. So you would have $10.42 gives based on your equilibrium of the member. You would have its summation of fx is equal to 0. This one 10.42, and at B you would have summation of fy, which is 50 gives, and this moment will be counteracted by another moment which is like this. 10.42 into 12 is how much?
25.04.
125.04 foot kick. Yeah, that is what we have. Now it's up to you. We said that clockwise is positive. Okay, imagine clockwise is good enough. That's a good convention for us. Normally, most of the books adopt clockwise as positive shear. So we will also adopt the same one. So it's the most common assumption. Yeah, so this is what? Counterclockwise. Is this counterclockwise? So you just have to do nothing. This is a straight line and this is negative. 10.42. Yeah, and 10.42. This is your shear. Yes. And your moment is. Now, we will draw, normally I tend to draw moments on the tension side, up to you whether you want to draw it inside or outside, doesn't really matter. So this one is 10.42 times what? Okay, so this is 125.04. Yes, and because this is 10.42, and then we have VB or something else. So let's not call it V. Let's call it and AE is Okay, so this is 5 feet, 5 feet. Now you take the opposite of them. Why? Because in order to ensure the equilibrium of a joint. This is 10.42. This is and then one okay. Now again you can draw the shear force and bending moment diagram yourself. Okay, but let us make sure that this point comes down to 0. So you can have 125. What is 50? So for at moment at C is equal to 125 like this, 50 and how much is that? 125 0
0.04.
yeah, so that is approximately 0. Okay, so this is 0. So that's what I was saying, that this will come down to 0. Okay, so that's how you want to do this. Okay, now the other problem which I want you guys to do is so it's the same problem which is having okay, so now you apply this triangular variable on this leg. This is the fourth one, and let me, should I rub this off? Okay, rub this off, yeah? Please, I want to, yeah, is that okay? Yes. I'll give you one more. Okay, so this is another problem where you have fixed and pinned connection. So what is the static indeterminacy? 3 plus 2, 5, and minus 1, minus 1. So you get 3 and then equation is 0. So this is a determinate structure. It has got a trapezoidal load on this side and hermetic on that side. Okay? Huh? Yeah, these are all in this side. 5. Yeah, 5. Yes? Please write it down. Huh? Can we take a picture? Yeah. Should I rub it off now? Please hurry up, guys. I can't wait for you. We can't. Okay, you copy it. Okay, most of the people have copied. I don't. Okay, is that okay? Okay, so now we have another chapter which is called drawing influence line diagrams. Okay, this is a new topic for you guys. Okay, and we shall start this one from today. Okay, so now so far you have seen from your structure analysis that we had a stationary situation in the case of applied load. Sir, excuse me, can I have your attention please? Okay, so far what we have seen is that the load which was applied on the structure, be it truss structure, be it frame or a beam, whatever, that was stationary. We had a static situation where a beam, a frame or a truss structure was subjected to some static set of loading. Okay, so in other words, the load was not changing its position. Yeah. Now we are going to study what happens if your load changes position with respect to time. Okay, what happens if the load is changing its position? So in other words, your structure is static, it's not moving, but the load on it is moving. And when can we have that sort of scenarios? Yeah, I mean, like, for example, mostly it is on bridges. Now, if we are designing building structures, okay, building structures, which is obviously building structures are occupied by human beings. Human beings always move around, so yeah, that can be considered as a moving load, but most of the time they are stationary, okay, in buildings. And that's why we don't design buildings considering the load of human beings as moving loads. We just say that this is a blanket load which is applied on the whole structure, okay, and we multiply that with some factor, we factor it up. Why? Because obviously if I'm standing over here, okay, so I will have a static load, okay, which is running into the ground. But if I'm moving, the same load is moving, so then then the structure will be experiencing more load because of the dynamic effects. Okay, dynamic effects enhances the applied load, isn't it? Yeah, if you have a stone in your hand, okay, that has got, okay, and so, and you are holding it, okay, and so that your hand will experience a particular sort of effect under the static stone. Now what happens that, or imagine, forget about stone, imagine I've got a ball I'm holding in my hand, and that is one effect, okay, but if someone chucks the ball at me and I try to catch it, my hand will experience different effect, isn't it? Because, and that is more as compared to the static effect, isn't that? So therefore we have in the dynamic effects enhances the load magnitude, and we consider in our building structures that we apply, we consider the live load as a static load, but that is factored up, okay, that, but so in the case of human beings it's okay, I think works for you. But if you have a very big dynamic loads, like for example, big can be like movement of vehicles, okay, that dynamic load you can't just apply a blanket factor on it and enhance the static capacity, okay. So what happens is that we consider then the effect of that moving load on the structure, effect of the moving load on the structure. Now what happens is that, for example, if I have a simply supported beam which is subject to an applied load, some applied load, yeah, in the static condition it will give me shear force bending moment diagrams, and we will study later in the course that you can find out deflections also under this load condition. But you would appreciate that if I change the position of this load, my shear force, bending moment diagrams and everything changes, doesn't it? So does that mean that I have to do, I mean, like, in order to study the effect of moving load, I have to do multiple static analysis? Yeah, I mean by multiple means, like I have to do then the infinite static analysis in order to find out, I mean, the effect of load as this moves. Okay, so what happens is that so I mean that is very time consuming, isn't it? So something called influence line diagrams then come to our rescue. It gives us a picture, it tells us like what the magnitude of the load, what the magnitude of a particular quantity of interest would be when your load is moving. Okay, this comes now. Influence line diagrams, they are not shear force, bending moment, or deflection diagrams. Okay, they are not that, but they look like one. They look like that, but they are not shear force or bending moment diagrams. Their function is that they give you the magnitude of your quantity of interest, which means your reactions, moments, or anything like that. Okay, when your load is moving, that's their function. Okay, and so what we are saying is that we have to find out shear force, bending moment diagrams, and deflections when our load is moving. It's changing its position with respect to time. That's what we have to find out. Okay? And you will see now like how we can find out using the concept of influence line diagram. Do you understand the concept? Do you understand the complication like what we have? If we use the same technique, the same static analysis technique for finding out the scenario when the load is moving, then that's not really possible. It is like because you have to draw then infinite diagrams. So in order to avoid that, we use something called influence line diagrams. Okay? Is that okay? Any question? Okay, so how would we find out how would we draw our influence line diagrams? You have to understand few things before drawing influence line diagrams. Influence line diagrams are linear for determinate structures. In this course, we are doing determinate structures, and hence they are always linear. Okay, so whatever you draw, that is linear. Okay, so that thing you have to keep in mind, that influence line diagrams, they are linear for determinate structures. Now, in order to draw influence diagram, we use a principle which is called, which is called Muller and Breslau principle. Okay, Muller and Breslau principle is used to define your influence line diagram, and I'll give you that principle first. But before going there, okay, let us use some common sense. Okay, let us use some common sense. Imagine I have got this beam which is simply supported and subjected to a concentrated load. Okay, this load, this might be a bridge. Okay, and imagine this load enters over here from this support and it moves. It starts from here and it moves till here. Okay, this load is variable. If I want to find out reactions, if I want to find out my reactions along the whole structure, okay, how would I do that? There is equilibrium equation. But first of all, why are we interested in finding out any quantity of interest whilst the load is moving? Why are we interested? What do you think? Why are we interested? What's our objective? Why are we interested in finding out the quantities or any quantity of interest like reactions, like bending moment, shear forces and all that when this load is moving? What is our aim? What do you think? Our aim is to find out that position of this load which will give us maximum magnitude of that quantity, isn't it? If I know the maximum, I can design this structure based on the maximum, and I can be rest assured that this structure will work for any position of this load. That's what our aim is, isn't it?
Yes, sir.
So we want to find out the maximum, that particular location which will give us the maximum load. Yeah? And what do you think? Where should this load be located in order to give me the maximum reactions? Okay, very good. Center. So this should be located at center to give me maximum location. Everyone agree with that?
Yes, sir.
Everyone.
So half of reactions होते हैं.
Yes, but that gentleman is saying that it should be end. Does it make sense? No, it doesn't make sense. How are you saying that it should be at end? I mean,
give maximum reaction at one side.
Only.
At zero at the one will be maximum.
And then
no, you're not making sense. Like, look, all of us, we are disagreeing with you. Yeah?
maximum value.
You're not making sense, really. You're not making sense. Look, we are all these intelligent people. We disagree with you. Yeah? Look, guys, just use your common sense. Simple common sense. If it is in the middle, half will go there. If it is at the end, how much will go to the support?
Maximum.
So maximum has to be at the end. It has to be at the end, isn't it? The moment it enters, for example, I'm walking, and these are two supports, The moment I'm stepping on that support, that is the maximum load which goes there. The moment I cross that support, then some load proportion of the load will go to one support and another proportion will go to the other. So then that maximum magnitude will keep on reducing. So, would I be wrong in saying that this one, if I draw something like this for the reaction, imagine this is normally, the load magnitude is normally taken as unit, okay? And that unit load is then moved along the whole structure. But if it is over here, I will have a maximum load of this one. Yeah, maximum magnitude. And so we are talking about, if this is A, this is B. We are talking about the reaction at RA. So RA would be 1 when it is over here. Agreed? And what will be the value of RA? Imagine this is length L. And this is X. Yes? So, what will be the value of RA when the load is at a distance X? RA. So can I write it like this? Can I write like this?
Yes, sir.
I've just taken a moment about this point. Okay, RA times L into 1 times L minus X. That's what I've done. So I can write, so this is a linear equation. Agreed? This is a linear equation. And look, when this X is equal to 0, I get 1. And as it starts moving, the magnitude of this 1 reduces by this proportion, L minus X by L. And when it reaches B, what happens? So you will have 0 load on this one. Is that okay?
Yes, sir.
And similarly, we would have for RB, we would have the same. So this is something which is called influence line diagram. Okay? This is something which is called influence line diagram for the variable of interest. And what is our variable of interest in this case? The reaction. The reaction is something we are trying to find out. So that is our variable of interest. And this is called influence line diagram. So what does this diagram tell us?
The maximum magnitude of load.
No, not the maximum necessarily, the magnitude of load. The magnitude of what? No, the magnitude of reaction. It tells us the magnitude of reaction when the load is moving along the beam. Okay? It is the magnitude of the reaction at point A, this one, and at point B. Okay, not exit and entry. It is the reaction. Like for example, what is this thing? This is also, what is this thing? For example, at some distance, what is this? This is the reaction at A. When the position of the load is where? X. For example, if this is, if this is my XA, so this is the reaction at A when the position of the load is at XA. So this length, so as you move along, okay, this tells you that this is actually with respect to the position of the load. Okay, so this is, so please notice that, okay, focus on this, that we have this thing. This is actually if you take the magnitude of any, if you take the value of this this diagram at any point, that is actually the magnitude of your variable of interest when the load is at that particular point. Okay, so that is important.
Sir, if the load is at B,
if the load is at B, then it becomes
the
0.
reaction at B need to be maximum.
Yes, so that's what I have written. No, this is for RA. For every variable, you will have different influence line diagram. Look, bending moments and shear force diagrams. This tells you moments and shear along the whole length. Okay, isn't it? In this case, the influence line diagram is corresponding to the variable of interest. Okay, so it is for a particular variable of interest. So if you have even the influence line diagram for a moment or for a shear, that would be moment or shear at a particular point. Okay, that would be the moment or shear at a particular point for the variable load. Okay, so if I give you if this was for example, a moment diagram, that would have been the moment at a particular point, okay, when your load is moving. This is not for the moment, this moment or shear for the whole beam. However, your bending moment and shear force diagram, that is for the whole beam. That's why I told you that influence line diagrams, they might look like bending moment or shear force diagrams, but they are not. They are not shear force and bending moment diagrams. Why? Because shear force and bending moment diagram, they are for the whole beam. If you have a bending moment diagram like this one, that would be a particular point, would be a moment at that point, isn't it? Then as you move forward, another point. So that is a bending moment or shear force along the whole length. However, if I draw my influence line diagram, that would be bending moment or shear force for a particular point when your load is moving. So the variable is when load is moving, that is with respect to the moving load. Okay? Yes.
सर जो आपने आरबी के लिए ट्रायंगल बनाया है उल्टा नहीं बना
नीचे वाली साइड
What do you mean? This is RB, and when your load is over here, that is maximum.
सर मैग्नीट्यूड कहां से मिलेगा
Sorry?
एक्सिस क्या है इसका सर? मतलब सर हम
No, imagine we are talking about this one is positive and this one is negative. Above the line is positive, below the line is negative. So your bending moment for RB would be sorry, not the bending moment. The reaction for RB would be X over L, isn't it? What is RB? 1 into X by L, isn't it? RB is equal to 1 time X divided by L, isn't it? Is that okay? So when my X is over here, when X is equal to 0, RB is 0. And as X increases, RB increases. And over here, RB is 1. So,
Suppose the 0 point I cannot.
sorry.
Are they both graphs on the same axis? Yes, sir.
These are the Sorry?
पहले वो वाला ट्रायंगल छोड़ देते जिसकी वजह से लग रहा था कि दोनों पे मैक्सिमम
This one?
Yes, sir.
No, not this one. This one. This one. Okay? Okay, so I'll write now something which is called Muller-Breslau principle. I'll write the definition of that. Should I write it off?
Yes, sir.
Okay, so in order to determine or in order to work out the influence line diagram, we use this principle which is called Muller and Breslau principle. Okay, and this principle straight away tells us what the influence line diagram is. Okay, and we understand how this principle works. But let us see what it says. The deflected shape of a structure. Okay, the deflected shape of a structure represents to some scale the influence line for a force effect if the quantity in question is moved through a small unit displacement. In other words, so let us break it down. Okay, I know it's a mouthful, but let's break it down. This is the deflected shape. We know the deflected shape. Okay, so there is something which the deflected shape has to do with the influence line. The deflected shape of a structure represents to some scale, okay, the quantity, the influence line for a force effect if the quantity in the question, which is like if the influence line for a force effect, if the quantity in question, that means that a quantity in question is the variable of interest. Okay, shear force, bending moment, deflections, reactions, all that is moved through a small unit displacement. So what it means is that if I have a structure, yeah, I can, and I'm interested in finding out the reactions, for example. My quantity of interest is finding out the reactions. So the support whose reaction I'm interested in, I will remove that support. Okay, then what will happen in the case of determinate structure? That structure will become unstable. So if I remove that reaction and I move it by some displacement, okay, in the opposite direction, of the of its deflected shape, then I can get the influence line diagram. Let us apply. Let us see what it means. I have got this structure, okay, which is a simply supported structure. Yes. This is my simply support. I am interested in finding out my reaction at A. Yes. So the restraint which is applied to A, I remove that. So this will become unstable and it will come down. Yeah. I won't allow it to come down. I'll try to move it opposite to its direction in which it is coming down. So, in other words, if I have this thing, I move it in this direction by a unit displacement 1, and I will get my influence line for this. This unit deflection, this deflected profile is actually my influence line. Let us do it again. Okay, let us do it again. What we are saying is that if you have any quantity of interest, okay, in our case for the time being, for this lecture, it's just reaction. Next lecture it will be shear and moments, but in this lecture it's reaction. So if we are trying to find out a reaction, yeah, what we do is we can apply the Muller and Breslau principle. And how do we do that? We take the same structure, which in our case is the beam. Yeah. We first of all find out what we are interested in. So we are interested in finding out the reaction at point A. So what we do is the restraint which is at that particular point, we remove that. Yeah, you remove that. So what will happen? From our previous knowledge, we know that this is unstable and it will try to move down. Yeah, it will try to rotate downwards. But we don't allow it to rotate downward. We apply the unit displacement in the opposite direction of the one in which it is moving. Yeah. So what happens is that we move it in opposite direction by a unit displacement. So this is our unit displacement, and we will get the influence line. That deflected shape is actually the influence line. So that's why he's saying the deflected shape of a structure represents to some scale. This is our scale. We move it by unity. The influence line for a force effect, if the quantity, this is for the force effect. Force effect can be shear, bending moment, reactions, all that. In our case, it's reaction. So, the influence line for a force effect, if the quantity in question is moved through a small unit displacement. So, we have moved it to a small unit displacement and we get our influence line. Any question about this one? Have a look at it and please tell me if you don't understand.
सर इस इन्फ्लुएंस डायग्राम पे लोड की वैल्यू का कोई इफेक्ट नहीं होगा.
Okay, you are asking that the load effect won't have any value, the load won't have any effect? No. This principle is just saying, forget about the load. Just try to find out, first of all, you understand what you are after. So the first step is, I am after reaction, finding out reaction. Okay, that's it. That's my first step. The second step is, what restraint is applied at that point. Remove that restraint. Okay, and you remove that restraint and then you apply unit displacement at that particular direction. Okay, and if you apply unit displacement, you will get a deformed profile. That deformed profile is your influence line diagram. Okay, so either you can use the first principle which we did over here, using equilibrium you can find out your influence line, as I told you, or you can use Muller and Breslau principle. Okay, this principle makes our life very easy. Why? Because it will straight away give you the magnitudes and everything. Okay, rather than going through the rigmarole of finding out, using equilibrium and finding out like your reaction. Okay, so this doesn't have the answer to your question is, this doesn't have any effect on the applied load. It is just about the deflected profile. But we are doing it currently for the determinate structure. For determinate structure, as I told you, the influence lines are linear. You can easily move it, okay, and you can find out your influence line diagrams. For the indeterminate, it's not linear, but that comes later. That's not in your current scope. So that's how you apply your influence line diagram. Ask me any questions. Okay. Let us. Is that okay?
Yes, sir.
Okay. Should I rub it off?
Please use this side of the board.
Should we use this side? Okay.
Yes, sir.
now, for a simply supported beam, this principle is very straightforward. Let us apply it on a bit more challenging beam. So I've drawn this beam, a two-span beam, again a determinate beam. Why? Because we have got a pin in the middle. Okay, but we are trying to find out the inference lines for A, B, and C. This is a pin.
Supported C is it roller or pin?
C वाला
This is a pin. It can be pin or roller. It doesn't matter. Why? Because we are just doing vertical load. Horizontal is not in question. Okay. So we are doing just vertical. We are just.
तो नहीं है चलो अगर हम दो पिन कर देंगे तो फिर तो ये
No. But I'm saying that we are not considering, so it doesn't matter to us, does it? If you are not considering the horizontal, we are not trying to find out the horizontal load. You don't have in influence line load running horizontally.
लीनियर तो नहीं अभी होगी आप नहीं करेंगे डिटरमिनेंट के लिए होती है
Yes, but this is determinate for vertical load. Is it not determinate for vertical load? This structure is determinate for vertical load. This structure is not determinate for a horizontal load. Okay, it's not determinate. Horizontally, you can have, for example, some waves generating and that moving, but we are not taking that. We're just taking vertical load. Okay, so this is determinate for your vertical load. I mean, you can take it as a roller, but the problem is that you have got roller and over here you have got hinge. That is not realistic. Okay, why? Because your roller can move in this direction and this area can be problematic. Theoretically, yes, you can do that. Okay, but practically it's not possible. Okay, so that's why I take it. But always look at the load, applied load, and then see whether it is whether you have horizontal. Most of the cases you won't have. Yeah, but I mean like it doesn't matter. Okay, now you guys are going to help me draw the reactions. The first reaction is A1. What should I do?
remove the support at A
Remove the support, then okay, move it up. So then
intensity load की नहीं given तो कर देंगे
no. I told you it's always a unit load.
unit load
It's always a unit load. Why do we consider unit load? Because whatever the magnitude is, you can multiply the inference line with that magnitude and you can find the required magnitude. So it's not important to get the magnitude of the load. Okay, we always do it for. So what will happen? Okay, first of all, let us see which points would have won't deflect.
BC
B, so let us draw it, okay? Let us draw, so B shouldn't deflect and C shouldn't deflect.
0 constant line
Is this a constant line? And this one should be,
triangle
so what do you think? What should we do? Linear, yes. Linear, you're right. So let us draw a linear. Now, Is that all? Because remember, you have to have, the other parts. Okay, this is a deflected profile of this. Okay, this is a deflected profile of this. So these other parts, they won't move.
They won't move, sir.
Sir, we are talking about
Can this point move or not?
Yes,
This can move.
This is a pin. So this will move. And then this is
Can you explain this?
Look, please make sure. Look, first of all, the first step is that you pick up those points which are going to be zero, and then you pick those points which can move potentially. Yeah. So first of all, those points which are zero and those points which can move. So I have this point which can move. Obviously, this is what I'm interested in. I have got this point which is zero, but this point can also move. So this is like, this is like it's like a seesaw, isn't it? This point is your pivot, and about that pivot, this section, this thing can move, isn't it? This is just like a seesaw. So it can move, but this thing can't move because this is just a link. So this thing can't move. So this has to be zero. So this is just like a seesaw, okay? This can move.
Got it.
Is that clear?
Yes, sir.
Is that clear to you all? Yes? Sorry? No, but B and C are supports. How can B and C move? I told you, you can't, look, this is like, if you're trying to find out the reaction at A, so you're not gonna allow B also to move. Okay? You don't saw the same branch on which you are sitting. Yeah? So obviously, because everything will then move. So you have, so this B and C, they can, because they are not, you're not trying to find out the reaction. Only this point can move, and this point can move because of pin support. No, then it's an indeterminate structure. This is an internal pin. This is internal pin. This is an internal pin.
ट्रायंगल जो है वो एक छोटा ही बना है कि
Sorry?
ट्रायंगल जो है ये वाला छोटा बनाया है मतलब
Why is this small? But this is length is big. Dig it. Once you find out one, you can find out your magnitude, the magnitude of all these or not. If this is 1, what is this angle? You can easily find out this angle. And this perpendicular by base is equal to this 1 by this. So you can find out the magnitude of this one. You can find out the whole figure, everything in this figure. Can't you? So you will find out everything over here. Okay, because this is a small triangle and this is a big triangle, that's why. Is that okay?
बी पॉइंट पे समेशन ऑफ मोमेंट 0 थे हमने एक इक्वेशन बना दी थी रिलेशन बना दिया था आर रिएक्शन के तो उसमें हम रिएक्शन इसका मिरर बनेगा कैसे बना रहे हैं समेशन ऑफ मोमेंट एट पॉइंट बी दे दें
Look, in order, if you want to, this is by using Muller and Russell. principle. But if you don't want to use this principle, then you put it over here. You know that it is linear, isn't it? Yeah. So I'll put it over here. I'll get 1. I know that this will be 1. Then I can put it in the middle, okay, and find out my reactions. All the reactions. I will do my structure analysis and find the reaction. So I'll find out the middle one. Then I can do it for this one also. I can put it over here at one point between the plastic hinge, between the hinge and the point B. Yeah, I can put this over here and find the reactions again. Yeah, so I will find this one, and I mean, like, you know, so I can find this magnitude, I can find this one, and I can find this one. So I mean, I'll find everything. So if I want to do using structure analysis, I can do it. Yes, you have to find out reaction. Okay? Okay, now hurry up, guys. Let's do this one. How would we do this one? A is 0. B maximum. B can be variable, and C is 0. Now what will happen? This can move. This we don't know, but this one can move either in this direction or in this direction. I have to move this upward. This one will just follow the deflected profile. Okay, this one will follow. So this we don't know. So I have, but this one will be 1. Okay, so I can join these two. I can join these two. And what will happen?
That's straight line towards 0.
Straight line towards C is impossible.
No, sir. Linear line towards C.
Straight line होगी,
This is a straight line. And in this one, this one is 0. This one is 0. This can move like this or like this, and this one is 1. You try. No, what do you mean? This will come down?
Yes, sir.
Huh? No, you have this link. You are moving it like this. So how will this come down? This you are moving up like this. Then how would you mean this whole thing will come up? Can this whole thing come up?
C point है हमारे पास लाइन को B point yes sir D point C से D के लाइन
अच्छा
और फिर कांस्टेंट होगी
फिर जीरो रहेगी
सर B तक जानी चाहिए
कैसे B तक जाएगी? अगर ये B तक जाएगी, you are again releasing your.
Straight point till P.
No, but you mean this will come like this?
No, sir.
Are you saying like this?
Yes, sir.
Huh?
Yes, sir.
Are you saying it should come like this?
Yes, sir.
Yes, sir.
No, sir.
But how would this rotate about this?
This won't rotate, sir.
No, but you are breaking it over there then, means. Again, if you are rotating it like this, so you are assuming that this is a, you have put a pin over here, but that pin is not there. So this can never be like this. This will be like this, and then it is constant.
For the B part, for the B supply, we have maximum load of 1 unit. Then how
This is one. This is one.
How is it increasing the
No, how do you know maximum load? You don't know. Maximum load is 1. Yes. But this one will go. Huh? So what? I mean, like, even if it's greater than 1. If in this case, there is a possibility that it goes further. Why? Because you will have a bigger force, and then that bigger force you will have an opposite force back. You understand? You should do the structure analysis. And in structure analysis, you will find that one of the reaction is higher than the other one. And so overall summation of Fy is 0. So this is possible. Sorry, excuse me. Yes? The reaction B. Excuse me. Reaction at B. Okay. Obviously, this is 0. This is 0. This can move up or down. And this point we move by unity. So if we move this by unity, what happens? This will go like this. And this can take, you can rotate it about this point. Yes? So you have moved it like this. So what will happen? This thing can easily move higher. This point can easily move higher. And then after that, this is joined with this one. Why? Because this is the pin set. Another pin is over there. So this is then connected to your pin. So if you want to move it in this direction, you will have this sort of profile, reflected profile.
Yes.
This is one link and this is another link. There are two links. Yeah, there are two links. I have moved it like this, so it will be like this always, isn't it? You can do that experiment. You have got two links. One is this link and another one is this link. Yeah, and they can rotate about this point. So if I move this one like this, so obviously it will become like this, isn't it?
Yes, sir.
Yes, sir.
So that's what I'm saying. Yes. Thank you very much. Thanks a lot. Thank you.